YouTubers, I'm back again with video number 5, and this is another look at the Diels-Alder cycloaddition. In the prior video, I showed you a particular workup after the reaction is complete. Now we want to look at a different approach, you see, because the product of the reaction we're doing is a solid at room temperature. Okay, this will load in a minute, and we're going to go to the Diels-Alder on the right there. And like I did the last time, we're going to take the quinone, 2,5-cyclohexadiene, 1,4-dione. You can, in principle, do a double Diels-Alder here. This is your dienophile. But we're going to look at the mono-adduct, which can be done. So we're going to react one side of the compound, but not the other. So I'm going to add that. See, it's a solid, the starting material. And the conjugated diene we'll use is cyclopentadiene. That's usually made by cracking a dimer at a high temperature over 200 degrees and using it in situ. I'll double click on that. See the color when you mix them. And I'm going to do it in nonpolar solvent, represented by ether, diethyl ether. There are your 3 materials in the round bottom flask shown on the blackboard. I'm going to bring it over to the stir plate, and we don't need a catalyst for this reaction. Some Diels-Alders do, but the one we're looking at here in the virtual lab can proceed with heating without a catalyst. We're going to attach a heating mantle. Reflux condenser, nitrogen gas. And let me move my mouse. There it is. You can see it. And we'll start. Note the time on the clock. You can adjust that at the start. Isn't that something? I'm in Eastern time. My clock in my room here says 4:13, and that's the exact time on the laboratory clock. Now, while that's heating, you can advance it. First, we'll do a TLC again. And you can see over on the blackboard, we are getting reaction because the product of the reaction, I'm putting my cursor on that, shows you the mono-adduct of the Diels-Alder cycloaddition. I'll click OK. I'm not going to save this, but if you were, you'd open up the, you'd click Save, and then OK. And then when you open up the lab book, you'll have your TOC stored, along with the reaction, the date, and the time of the reaction. I'll X that out. Let me go ahead an hour, and I'll do a TLC and see if it's done. Nope. I'm still going. I'll go ahead 10, 20 minutes. Still there. Let me get bold and go another hour. It's done. So I cheated and went a little bit further ahead. If you left it alone, it would proceed to give you an idea of the amount of time needed in real time. So I'll click Save, then OK. Now, we have diethyl ether, and we have the compound, the product, which is a solid. You see it there on the blackboard, the solid. So we're going to take this flask and put it in the SEP funnel. And in there we have the solvent and the Diels-Alder adduct. I'm going to then move that round bottom to the cork ring. It's a product mixture, and we're going to do that by putting that on the plate. Ah, they want us to wash it first, I guess. So let me put, I don't know why, but let me put some water in there. Ah, okay. You never know. It doesn't hurt, right? You're going to wash it. Now, the lower layer is the water. There's nothing in it. I learn something every time I do one of these runs. The upper layer is the solvent and the product. Now we're going to take that upper layer, move it into a cork grain. Presumably it's been dried with drying agent and filtered. Now, by me moving that over, that ether has been rotovapped off because that's a solid product that you're going to get. So let's do an infrared, and there's the infrared of the product. Now, normally I would have students look that up in the SDBS structural database online, where you can retrieve spectral data. You could put it in the notebook, but I'll just exit out. Now, let's look at the proton NMR. Okay. And we'll click on the H, the proton NMR, to go to C13. And there are the chemical shifts. It's a decoupled spectrum, so we're only getting the chemical shifts. And there's your carbonyl, about 200 in the product. Okay. Let's see, mass spec, fragmentation pattern, and the molecular ion is the base peak. That's an interesting one, huh? Now, that's a solid. Let's see if we can do a melting. I haven't tried this. Going to have to look into that. I don't see any melting point going on there. So I'll have to investigate that. Nope. Not doing melting point. So anyway, I'll look into that and see if that can actually be done. I think that would be done if you're doing organic structure determination in another component of the virtual chem lab. That's what I think it is. But anyway, that's how you do it here. If you have simply a product in, let's say, diethyl ether, when you move the round bottom into the sep funnel, wash it, you take your top layer, bring it down, the ether will presumably be rotovapped off, not shown, leaving you with the solid product. In the last video, I attempted to heat it, and there's no point in doing that because it's going to be a solid product. So anyway, that'll give you an idea of the types of things you can do. And in fact, when you're first setting up the reaction to start, you can hit on that bell and your help section will open up. You can advance the time on the reaction, but if you do it too fast, the glassware could explode. So it's you should err on the side of caution. Try it a few times, you'll see what happens. If you're doing a reaction like an alcohol oxidation, using PCC, then you would do the reaction in ice bath, or a Grignard reaction, let's say, if you didn't want to heat it. And we'll do that in other videos. Thanks for watching. Bye for now.